Good morning, everyone. Good morning, San Francisco. Um, Today, we're going to be talking about what does recomposition mean to your app. My name is Aida Issayeva. I'm an Android engineer and also Google developer expert. Um, that's about it. And so, when we talk about recomposition, we have to understand how recomposition works in general in Jetpack Compose. Understand what are what are some gotchas and catches that we need to learn about recomposition? What are some tools we can use, to debug and monitor recomposition? And then later we will discuss about some practical tips we can use as a developers to leverage and limit the recompositions. Historically, Android views were represented as a tree of widgets, where in order to update the element, you would need to go through the tree, find the relevant node, pass the new argument via like getters and setters that are exposed, and update the internal state of that UI widget. But that approach was prone to errors since node could have been removed at a time when the update came through. So in Jetpack Compose is a declarative UI framework, meaning UI widgets are functions. They're not objects, as it is in Android View. There is no internal state held, and the only way to trigger the updates is by passing different arguments to those functions. Jetpack Compose has built a substantial machinery to detect those different arguments and trigger updates, not only in terms of single composable function, but the entire app. So how does this machinery work? Let me give you an overview of the most important parts of it in terms of recomposition. Android operating system itself is built as a tree of widgets. Unlike Jetpack Compose has a state snapshot system in place that communicates directly with Android operating system via observers and subscribe to user interactions that usually drive a change in the state, hence the name state snapshot system. All of those state changes are passed down to composition, where composer produces the next list of changes based on the information inside the slot table. Slot table is sort of in-memory cache data structure that contains the latest and the up-to-date information about the composition. Once composer produces that change list, it records the information back to the slot table because it would need to update the slot table with the latest state, and then applies changes to the UI node tree that in return gets attached to Android view tree. So this is how entire composition machinery works in place. So let's dive into the foundation and get better understanding of how recomposition works in Jetpack Compose. When we talk about rendering of UI widgets and seeing the final results on the screen, it is important to keep in mind the phases each widget goes through. In Jetpack Compose, there are 3 phases. Composition, what UI to show. It basically creates a description of UI widgets. Layout, where to place UI. It measures and places all the child nodes in a single pass. This is where modifier functions start coming to play. And the drawing answers the question how it renders all these UI elements. The order is always preserved, although some sections may be skipped. So within these phases, Jetpack Compose has also its own layers, where every layer is responsible for a specific part. Important to note, these layers are separate modules. Runtime and compiler are hearts of the composable, compose, and responsible for running the declarative machinery in place. And they are platform agnostic, meaning as long as you write your own UI layer, runtime and compiler can be used in web, iOS, and all other platforms. So UI layer is an essential communicator between Android operating system and Compose world. It is aware of Android lifecycle, instant changes, context, accessibility, and so on. Because UI layer is an integration layer between Android platform and the Compose, it is also responsible for executing all these composable functions, and it's done via set content Lambda function. On the other hand, it's also responsible for passing down all the platform-specific information like context, configuration, lifecycle, save instance, save state instance, and so on, all the way down to Compose runtime via composition locals. After the set content is called, all the relevant information is passed down to runtime. Compose phases and layers begin to play in the runtime. Runtime is a vital component of Jetpack Compose that contains all the logic and execution. And within runtime, there are three important classes to keep in mind when it comes to recomposition. First one is a composition class. Note, it is different from the composition phase. Composition class contains the slot table, composer, change list, and so on. And the constructor of composition class expects a recomposer class and applier class. Recomposer contains state snapshot system and list of composition classes. Applier is an interface that is responsible for materializing UI and seeing the final result on the screen. Let's take a look at Recomposer and learn what's its job at the composition phase. When we think of Recomposer, we should think of it as a scheduler that is responsible for triggering, awakening that composition phase, and passing down the updates to the list of compositions. And because Recomposer contains the state snapshot system that observes OS changes, in the UI layer, we have a window Recomposer file that initializes lifecycle-aware Recomposer. The initialization happens in Android's view extension function, and because it is Android's view, we can locate a lifecycle owner of the view and attach the lifecycle observer. Notice in this code snippet, in onCreate event, Recomposer calls function run recompose and apply changes. This function registers an observer for change propagation. When that happens, this observer awakes, adds all of those changes to the snapshot system that ends up passing down the changes to composers. So composers can record the parts of the composition needs to be updated. In other words, this observer is the first state for triggering automatic recomposition when the state changes. So what does snapshot system exactly do? It captures state results at a specific read moment. Jetpack compiler wraps all composable declarations and expressions to automatically track snapshot read state within its bodies. This is how state snapshot is automatically observed. The goal is that every time the composable reads varies, the runtime can invalidate the recompose scope, so it executed again in the next recomposition. To visualize the snapshot system, let's have a composable function state snapshot system. The name is arbitrary, that contains two states, name and is important, and has a column with a checkbox and text. Let's assume we have passed all three phases, and now we see all three phases upon initial composition, and now we see the UI widget on the screen, with the checkbox and the text. Then we decide to toggle back and forth that checkbox. Recomposer observer has awakened because it noticed a user interaction and the state reading happened upon click, and because we changed the value of the state inside the onCheck change listener, the state snapshot reads two values for the state is important and one value for the state name. And then therefore, we're going to get three more state values. Then all of these state read results are propagated to the list of composition classes, where a composer identifies changed versus unchanged values in the states, then updates creates a change list and updates slot table. So what is composition class, this interface? It is a process of executing composable functions by storing them and the relevant information on a slot table upon initial composition and applying changes to the slot table node tree upon recomposition. In set content function, the entrance to the Jetpack world, when the recomposer is initialized, applier and composition are initialized too. Note, recomposer and applier are arguments of the composition class. So composition basically is a process of executing all of these composable functions. What is composer? Think of it as a manager that knows when to read, when to write to the slot table, knows when to produce change lists, how to produce that change list. So essentially, composer is a main puppeteer of entire this composition process. Composer itself is an interface that helps Compose compiler to talk to the runtime. Compose compiler and runtime, there are different modules. Slot table is a memory flatten array, gap buffer, that gets filled with the information upon initial composition, then updated upon the composition, and contains the latest state of the composition. It not only contains the information about UI widgets, but also all the information about parameters, sources, deallocation, all the different variables, and so on. Because slot table is a representation of the current state, let's take a look how it gets filled with the information upon initial composition. Let's assume we have a composable function card. Upon initial composition, once we called set content, once the function card is called, the slot table is created, right? Then composer adds a group 1, 2, 3 for the function card, composable function card. Then within composable function card, we have a column, right? Composable function. Composer creates another group 4, 5, 6 inside the slot table and adds that value. Within the column itself, we have also text. Because text does not receive a content as a parameter, doesn't have a content parameter, it actually does not create a group. Composer does not create a group for the text, and instead it registers the value of the text inside the slot table. Here's the button as well inside the column. Once the button is called, the composer creates a group 789. Because button receives another composable function as an argument, composer creates a group 789. And because we're passing click listener is added to the slot table. And the last one is text inside the button, also added to the slot table. So what we see here is, although function card, inside there's a column, and then inside column there's a text button, and within button there's another text. Although there are a lot of nested composable functions, at the end of the day, slot table actually gives a representation of them as a flattened array. It is important to keep in mind that slot table only records the changes, to get to that later state, but it doesn't actually display the way how we see on our screen. The composer reads the slot table, produces the change list based on the information in it, and essentially each change is a deferred action with access to applier and the slot writer, waiting to be executed. After the change list is produced, all of those deferred actions will start executing, meaning slot writer will write all the changes to the slot table, and applier will apply all the changes in the batch to the tree. Applier is responsible for measuring, layout, and drawing UI widgets. Once applier begins its work, the layout phase starts. So applier is basically an interface for materializing UI tree. And because it's an interface, applier has its own implementation inside the UI layer. It's called UI applier. That is aware about Android operating system and contains all the relevant node tree information about Android inside the UI layer via UI applier. So when we talk about the change list, and then later on, it's getting applied to the node, to the Android operating system, within the layout phase, there are 4 steps to keep in mind. First step being all the child nodes get added up to the root node via bottom-up method. So it means in this example of the same checkbox and text in the column, the text inside the button gets added, and from there, button gets added to the column, and the column gets added to the root node. Then after all those child nodes added to the root node, we start measuring the child nodes. But upon measuring the child nodes, all the relevant information about some constraints from the parent node come down to the child nodes, like let's say padding information, margin information. But margin and padding is almost the same. It's the same right now in Jetpack Compose. So all of those constraints actually get passed down to the child nodes. After child node receives all these constraints, measures itself, it actually passes down all this measured information back to the root node. And once the root node receives all of those measured information, it places the child nodes on the screen where they should be. And in the last phase of drawing, applier draws the UI widgets on the screen. That's where drawing, color, and so on information come into play. And this is where we're going to get the final result of text with a button and the text inside. So what is recomposition in this example? In imperative UI model, to change a widget, you can call a setter or getter of the widget, and you would change it in internal state. In Compose, because composable functions, they are functions, right? And then they don't hold any internal state information. The only way to update them is by calling them again with the new data. Doing so causes the function to recompose, means the widgets emitted by these functions will be redrawn if necessary with the new data. The Compose framework can intelligently recompose only the components that have changed. So essentially, recomposition is a recalculation of all the changes necessary to the composition state, which is inside the slot table, and the materialized tree in the applier, and scheduling all of those changes. So the composition is basically a re-execution of composable function in response to those state changes. So when we talk about recomposition, we also have to keep in mind whenever the recomposition occurs, all of those phases of composition, layout, and drawing will repeat all over again. So let's look at the example. Let's modify the previous example and introduce state value to show how recomposition works. Let's assume we have a counter state value, which basically counts everything. And we still have a column with a text, button, and inner text actually reads the state, the counter state. Let's assume we clicked on a button. Once we clicked on a button, we Jetpack Compose actually updates the inner text click meme, right? And it passes down value 1. And it also updates the state to be 1. Now let's look. What if we move this text to the? What if we move the reading of this value to the outer text, right? And we will do the same. Reading happens inside the text compose, and user clicks on the button. Once user clicks on the button, what we see is not only state did get updated, but it also the column itself did get updated. And within the column, all of the child nodes of the column, which is text and button, did get recomposed again. Note, inside the button actually, inside the button text actually didn't get recomposed. Nothing did get updated. So one thing to remember when it comes to recomposition is that recomposition, whenever recomposition occurs, it will search for the nearest parent scope and will update all the values inside because compiler cannot detect whether only one parameter changed or multiple parameters changed, and that's why it updates all the child composable functions within that scope. So that's one important thing. And because recomposition goes through the same steps of updating slot table, generating that change list, updating the node tree, measuring, placing, and drawing UI elements, and attaching the newly generated tree to the view, which is potentially expensive in terms of like time, computing power, and battery usage, and so on. To mitigate this cost, Compose intelligently chooses which parts are needed to be updated at any given time. And it's possible via smart recomposition. When we think about smart recomposition, we should think of it as an intelligent way to skip some of the recomposition of composable functions when the inputs are stable, meaning when the parameters of the composable functions are stable. So how do we define stable composable functions? Compiler has some rules around to determine which parameter is stable. So rule number one is making sure the result of calls for two instances to equal function, will always be the same for the same two instances. Rule number two, whenever public property of the type changes, composition will always get notified, regardless of the stable type. And rule number three, all the public properties of the type are also have to be stable. What does it mean to be stable property type? The compiler has a list of stable property types that it thinks it's stable. The first of it being primitive type, like integer, booleans, float, and so on. So they're always detected as defined as a stable type in the compiler. And the second one is a string type. String in primitive type, they follow the contract of stability because they are immutable. And then there's also a third option, when every property type that is annotated with a stable, consider it stable property type. Warning though, annotating multiple property types with a stable is not an optimal solution. Try to avoid to annotate with a stable all of your properties, because Compose compiler right now is still in active development and it's adding up a lot of support for different data types. So that's something to keep in mind. So what about custom data types? Because let's be honest, in reality, when it comes to Android development, we don't rely on primitive types or like string and so on, right? We all have a lot of custom data types. Jetpack Compose actually has an algorithm in place to detect and leverage smart recomposition for the custom data types, and it's called inferring class stability. What it does is it visits each eligible class, right? Annotates with this add stability inferred, helps the compiler to basically determine, what composable function to recompose. Although it is important to note that it visits only eligible class, right? Because there are exceptions to it. Most importantly, some of the types like enums, enum entries, interfaces, and so on will always gonna be considered as unstable. One important example when it comes to interfaces is collections, right? Collections like lists, maps, and so on. They're always considered unstable because compiler does not guarantee, does not know for sure, for a fact, whether this is a immutable or mutable version. You can still make array list and pass the array list to the compiler, which is a mutable list comparing to regular list, right? So that's why it is easier for compiler to determine that this is indeed unstable class. So now if we talk more about details about how compiler defines and decides which property types are stable and unstable, it all happens all the way down on a lower level. And Amanda and Josie gave a great talk on compiler and its mechanism behind how it works. So what are some tools that will help us developers to learn, understand, and recomposition better? The first one being Recompose Highlighter. Google Play team actually came up with a Recompose Highlighter that will show what composable functions keep getting recomposed multiple times, whether they are needed or not needed. And now Android Studio Electric Eel has a support for it as well, automatic support in Android Studio. But if you don't want to if you don't want to download and install Android Studio Eel, please go check out the code snippet below that you can add to your Jetpack Compose app. Second one, log statements. It's ancient and the most reliable way of detecting and understanding how basically everything in a code works, including the recomposition. I actually wrote a modifier function for the log statements that will print it out to you recomposition counter for each element, for each composable function that you can pass to. But if you really want to have like full analysis of how composable functions work, exactly how many times they get recomposed, what are some elements, and so on, it is important to run compose compiler metrics, right, on the release version of your Jetpack Compose app, because it will give you a full analysis. Also, once it gives you full analysis, it returns you a JSON file with a list of information related to your compose functions. One notable element, there is a red flag whenever you have a restartable composables, but not skippable. So let's look at this example. We have a 76 restartable composable functions and only 64 skippable functions, which means there are 12 composable functions that keep getting recomposed when they're not needed, right? So like we're making additional recompositions, unnecessary recompositions. Also, my team, my colleague Chris Baines, wrote a great article on the metrics and how to read those metrics, understand and improve the code in Jetpack Compose. As you saw in Smart's recomposition section, Compose naturally tries to avoid unnecessary work and unnecessary recompositions that will cause to repeat the phases all over again. But to help to compose even further, we developers can use some tips to leverage smart recomposition. Tip number 1, breaking down composable functions. There are different ways to structure functions, right? But more you break down those composable functions, the more you reduce the recomposer scopes, meaning the number of recomposed functions will also reduce. Here's the example. We have composable functions. Good greetings tip 1 contains a column with greeting composable function with 2 greeting composable functions. One way to build this one is also having a nested columns inside that main column, right? And create the same output. But the more you break down, the more you reduce that recomposer scope, meaning if for some reason we update we pass a different argument to like greeting 1 instead of Android, we pass Jetpack Compose, it is guaranteed that only the first greeting will get updated, recomposed, but not entire column, not the outer column with the other greeting. So that's something to keep in mind. Number 2, use the key composables. So here's a little bit of details. Runtime assigns a type, restartable or replaceable or movable to every group in composition. When the key is not set, runtime cannot determine whether this item in the list was changed or was it moved, right? By setting the key, runtime lets compiler to know about the unique hash code for each item in the list, therefore prevents the recomposition of all of the children and recomposes only changed ones. So let's say we have here's the lazy column. Lazy column actually, or any kind of lazy layouts, they have built-in composable function, built-in support for the key composable function, where you can call the key inside the items and pass it the unique name to it. So let's assume here we have a strawberry in the example, right? And it gets removed, but because we set the key after the strawberry was removed, only the lazy column, the outer scope was updated, but not the inner ones. If we don't set the key, what happens is everything below the strawberry, like blueberry and banana, they do get recomposed as well, because runtime cannot determine whether they got updated or whether they were moved or did indeed get updated. So then therefore, if you don't set the keys, they end up recomposing. Number 3, read the state value at the lowest composable function. By deferring the state read all the way down to actual consumer, like the child node and the child composable function of the state, runtime will recompose only that function and not the parent and subsequent parents of it. Let's assume we have like some sort of good inner column that has a two text, Android and Jetpack Compose, and then the second parameter actually gets updated into view system. And then we also have a outer column, right, that has an upper row information and also has a good row information. And within the good row, we have another row of icon, Android icon, and the column itself. One way for us to pass down that information is to pass the change parameter, which in our case is going to be a second parameter, pass directly to the good row. If that happens, the good row within good row gets recomposed, meaning the row inside of it as well does get recomposed alongside with the inner column. But if we actually pass down the reading process all the way down to like inner column, what happens is we reduce the number of recompositions. Number 4, using modifier lambdas. Whenever a state value, it's kind of similar to the third one about the state reading process, right? But whenever state value, like let's say we're reading the value inside the modifier function, right? The read happens right at that time, then therefore causes the nearest scope to recompose. In this example of the good greetings tip 4, we have a row, and then within the row itself, we have a modifier function offset where we update our y-axis. If we decide to call regular offset function, what happens is it's gonna recompose row and all the children inside of it right there. But because we know nothing else inside the row, no other parameters actually did change, what we can do, we can wrap that offset in a modifier lambda function and pass the value to it. That way, we know for a fact it doesn't get updated. It doesn't get recomposed. Only initial composition happens. Initial composition happens, because basically modifiers come into play during the layout and drawing phases, right? So we're skipping the moment, we're skipping the composition phase where the latest state is captured, right, and read. We don't need to know about them because in our example, only the modifier information is being changed. And number 5, utilizing derived state of. So if we have some object, right, that depends on a certain state, like that is frequently changed, all the composable functions, that read that object will recompose more than they need to. It is better to wrap those objects in the derived state to limit the number of recompositions. In this example, we have a height bottom bar, right? That depends basically on the list state that checks whether if list is in scroll, if the scroll is in progress, we want to hide that bottom bar and not to display. Because it's a frequently changed state, like is in scroll progress, it's frequently changed state. What happens is if we don't wrap the height bottom bar inside the derived state, everything, including scaffold, right? The top level, everything gets updated. The scaffold, its bottom bar, and the content, which is a lazy column, does get recomposed all over again whenever the value inside the height bottom bar changes. And it will change frequently. That's why it's important to wrap inside the derived state of. And also now there are some tips that are worth repeating again. Tip number 1 is no logic. Move any logic out of composable functions to view models, presenters, or any other lower level. Number 2, do not create dependable composable functions on the result of other composable functions. It is because Jetpack Compose does not execute composable functions in a order that is written. There is no guaranteed order of execution when it comes to composable functions. So that's why it is important to keep in mind that you don't modify some variables and properties in one composable function and read in another, like if you have a global variable that you modify inside one composable function, but then you read in another one. And most importantly, avoid any side effects in the composable functions because they can run in parallel, right? And the invocation might happen in a different thread than a caller. Instead, use callbacks. And that's the wrap for this recomposition talk. Most importantly, here's the resources that I used. It's a great book by Jorge Castillo, Jetpack Compose internals, also the composition source code, Jetpack Compose source code, and all the other articles. Also, I have a snippet to the recomposition tips if you guys would like to check how it works, see some good examples, some bad examples, and see it visually how recomposition works in place. Thank you.